Good evening, everybody. Thank you for coming. Welcome to the Island of Ideas public talk series. Tonight's discussion on Antarctic wildlife skating on thin ice is brought to you in partnership by the Australian Meteorological and Oceanographic Society and the University of Tasmania for National Science Week. I'm Dr Jess Melbourne-Thomas. I am the Tasmanian patron for National Science Week, and I'm also a senior research scientist with CSIRO, and it is my absolute pleasure to be emceeing for this stellar panel who you will hear from very shortly. This evening we are broadcasting live from Lutruwita, Tasmania, Aboriginal land, sea and waterways. In recognition of the deep history and culture of this island, the University of Tasmania and the Australian Meteorological, I knew I was going to stumble on that word, and Oceanographic Society acknowledged the traditional and original custodians of Lutruwita, Tasmania and Nipaluna, Hobart, the Palawa and Muanina peoples. We are gathered to share ideas and talk about our changing oceans at the Institute for Marine and Antarctic Studies by the Tim Tamili Minanya River Derwent, as they once gathered to share knowledge, stories and culture. Tonight we're discussing how the natural world is responding to one of our biggest modern existential threats, climate change. And as we do this, we reflect on those who came before us and lived in harmony with and cared for this land for thousands of years. We pay our respects to elders past and present and those who were forcibly removed from these lands and did not make elder status. We stand for a future that profoundly respects and acknowledges Aboriginal perspectives, culture, language and history, and for the continued effort to fight for Aboriginal justice and rights. So thank you again for joining us for the Antarctic Wildlife Skating on Thin Ice presentation, a topic that is critical not only to our understanding of Antarctica and the diverse life forms that reside there, but also to our broader understanding of global climate dynamics. It really is crucial to recognise that the changes occurring in Antarctica and the Southern Ocean are not isolated events in a distant wilderness. They're signals of what's coming for our whole planet. Antarctic ice sheets are under increasing stress. We're seeing warming and melting, and what was once thought to be a relatively stable region, particularly in East Antarctica, is now showing signs of vulnerability. And importantly, as you'll hear from our speakers, we've also recently seen quite an alarming reduction in the seasonal extent of Antarctic sea ice. And so our discussion tonight is going to explore how these changes impact the unique wildlife of Antarctica and the Southern Ocean, species that have adapted to some of the harshest conditions on Earth. But these adaptations have limits, and as human activities continue to drive climate change, the fragile balance that has supported these species for millennia is being disrupted. So our first speaker tonight will guide us through the vital role that the Southern Ocean plays in shaping Antarctica's future and its impact on global climate dynamics. It's my pleasure to introduce Dr. Ed Doddridge. Ed is a Senior Research Associate in Physical Oceanography at the University's Institute for Marine and Antarctic Studies. His research seeks to understand the Southern Ocean and its sea ice, which is at the centre of the global climate. Ed uses computer models, theory and observations to improve our understanding of the ocean around Antarctica and how it's changing. So please join me in welcoming Dr. Ed Doddridge.
Wonderful. Thanks for that introduction, Jess, and thank you all for turning out today. So, as Jess said, I'm here to give a bit of a background about the physical climate system around Antarctica and its role in the global climate system and the role of sea ice within that climate system. All right, so this is a map of the world according to an oceanographer. As an oceanographer, I think it's a travesty when we cut through all of the oceans and lay the world out flat. So this one, instead, we've cut through the continents and we've laid the world out. And what you can see is that all of the oceans are connected. We talk about the Indian Ocean or the Pacific Ocean, the Atlantic Ocean, but in fact, it is just one global ocean. And all of those ocean basins, the Indian, the Pacific, the Atlantic, they all connect around Antarctica. The Southern Ocean is the hub of this global ocean. So if we want to understand the global climate system, we need to understand what is happening around Antarctica. That is the center. It's where everything comes together. It's where we're mixing the waters from these other oceans. And so changes in Antarctica propagate around the world and affect our global climate system. So I know this is a bit of a weird map, but keep in mind, Antarctica lies at the center. So changes in Antarctica, changes in the ocean circulation around Antarctica will spread around the world alarmingly quickly. Now, the other thing that is happening around Antarctica is this seasonal growth and melt of sea ice. This is an animation put together by the Australian Climate Modelling Centre using satellite data from the late 1970s right up until today. And what you can see is the amount of sea ice covering the ocean on any given day back in time. So we're moving through the years pretty rapidly here. We're already up to the 1990s. And there are two key takeaways here. One, in the summer, there's not a lot of sea ice. Most of it melts away. And then huge amounts of sea ice forms every year. So at the summer minimum, it's about 3 to 4 million square kilometers of ice. That's still a pretty big area. It's about half the size of Australia. At its winter peak, it's about 2.5 times the size of Australia. So every year we're freezing about 2 Australias worth of the ocean surface to turn it into this layer of sea ice. It's only a couple of meters thick, but it spans such a massive area. And as this sea ice forms, something really, really remarkable happens, which is what this next video is going to show. As the seawater freezes, it expels a cold, salty brine, which sinks down from the surface ocean. And that cold, salty water is dense. It flows northwards away from Antarctica, and it carries nutrients and oxygen with it. And that water ends up filling up about half of the volume of the global ocean. As oceanographers, we talk about water masses, and a water mass is a particular flavor of ocean water. It has a particular temperature, a particular saltiness, and you can trace it back to somewhere at the surface of the ocean. So this Antarctic bottom water that forms around Antarctica sinks down to the bottom of the ocean and fills up half of the volume of the global ocean is a vital and crucial component of the global overturning circulation. The formation of this water is intimately tied to the seasonal cycle of sea ice. Somewhat alarmingly, observations and computer models suggest that this circulation has slowed down by about 30% since the 1970s. Projections pretty robustly show that it is going to continue slowing down into the future. That's not great news for the ocean circulation and the global climate as it is, but there's more bad news to come. Sorry. So this cold, salty water sinks down, fills up the global abyss, and is a crucial component of the sea ice cycle. Let's have a look at that sea ice. So here we're looking at anomalies. Every point on this graph is the difference between the amount of sea ice on that day and what we would expect from climatology, from the average. So we've taken the average to be 1981 to 2010 because you have to pick a particular time. And so when it's blue, that means there was more sea ice than you would have expected on that day. When it's red, there was less. Now, there are 3 distinct phases that you can see on this graph. From the beginning in the late 1970s through to about the mid-2000s, everything was pretty happy. It kind of bumped along. Sometimes there was a little bit more ice than normal. Sometimes there was a little bit less. In the mid-2000s, we entered this strange phase where there was a bit more sea ice. And you might remember headlines from the time where the climate deniers were saying, oh, climate change can't possibly be real. Look at Antarctica. Look at all this ice. There's way more than there should be. Yeah, all right, there was more ice. We didn't really understand it at the time. Now we're pretty confident that changes in the winds because of the ozone hole and extra melting of the ice sheets on Antarctica helped create an environment where we formed a bit more sea ice. But in 2016, it changed rapidly. And we went from this high sea ice state into a new low sea ice state. And since 2016, sea ice has been pretty consistently below that long-term average. The other thing you'll notice is that the variability has gotten bigger in recent years. Up until about 2007, the variations were fairly small, fairly short-lived. Since then, they've become bigger, they've become more persistent. These are two telltale signs of a regime shift. There's some pretty heavy mathematical theory that I won't go into tonight, but we can use that to explore this dynamical system. And it tells us that Antarctic sea ice is undergoing a regime shift. That regime shift is away from the historical variability that we saw and into a new regime caused by climate change. Again, that's not particularly good news. The last 3 summers are the 3 lowest that we have seen on record. But what has been particularly remarkable in the last couple of years is the wintertime sea ice extent. So what we're going to do now is we're going to take this graph, we're going to chop it up, and we're going to plot every year on top of each other. So we've plotted from January through to December. This is every year on that graph up until 2022. What you can see is that there are 2 periods where we have the most variability. Between about March and June, we have quite a lot of variability. That's where we're growing the sea ice. And when we get to the maximum in September, there's not a lot of variation from year to year. The wintertime sea ice has been remarkably consistent in the observational record since the late 1970s until last year. So what we're going to do now is we're going to grey out all of those. Those are the historical context. Keep that in your mind. And we plot last year. Yeah, I know, right? We actually ran out of ways to explain how weird this was. If you try and run some numbers, you can talk about floods as a 1 in 100 year event or a 1 in 1,000 year thing. If you run those sorts of numbers for something like this with some reasonably sensible assumptions, you end up with ridiculous numbers that range from about 1 in 7.5 million through to 1 in 700 billion. Obviously, that's not sensible. We only have 45 years of observational data, so we can't make claims like that. But I think it underscores just how weird and unexpected last year was. As it was unfolding, as a research community, we were scrambling. We were trying to understand what's going on, what's causing this. Is it going to happen again next year? And there was always that hope. Maybe this is just a weird thing that's happened. Unfortunately, this year in the black looks much more like last year than any of the previous years. Again, adding more weight to this idea that we have had a regime shift, that Antarctic sea ice has fundamentally changed, and that its role in the climate system is going to change moving forward. Now, we know that the climate projections very robustly show a decrease in Antarctic sea ice. That is very well understood. A warmer world has less ice in it. The good news here is that we know what's causing that. That's human climate change. That's our greenhouse gas emissions from fossil fuels. And because we know what's causing it, that gives us the power to change it and to fix it. So I want you to hold that in your minds as you're listening to Delphine and Barb talk, that everything that is unfolding is within our power to change. Is it easy? No. It is simple, but hard. Thank you very much.
Thank you so much, Ed. Very sobering stuff. That stunned silence in the room when you put up that red line from last year. Moving on to our next speaker, it's again my pleasure to introduce Professor Delphine Lannuzel, who is a leading expert in marine biogeochemistry and who also works with the university's Institute for Marine and Antarctic Studies. Her work focuses on the interactions between sea ice and the ocean in polar regions, investigating how sea ice stores and releases nutrients and trace metals, which are crucial for polar ecosystems. Her research not only enhances our fundamental understanding of polar biogeochemistry, but also informs policy and conservation efforts aimed at preserving these vulnerable and critical regions of our planet. So please welcome Professor Delphine.
Good night, everyone, and thanks for inviting us today. So what I'm going to talk about, that's a picture of me 21 years ago. First time I went down to Antarctica. That's my little feet there. As the icebreaker is breaking through sea ice, and I've learned a lot over the last 21 years, and I'll talk to you a bit about what we've been looking at. One thing that interests us is the life within sea ice. So Ed presented beautifully what's happening to the sea ice in Antarctica, and what I look at is the life within the sea ice and around the sea ice. So size does matter. So as far as Antarctica and Antarctic sea ice goes, as Ed presented, you know that the formation and melting of sea ice around Antarctica is one of the largest seasonal events on Earth. And as a consequence of being such a large event, it's also hosting one of the largest biomes on Earth. When you think about Antarctica and sea ice, you think about it's far away, it's white, it's pristine, it's probably not a lot going on within that environment. But it actually covers a wide range of wildlife, from the iconic species that you all probably know, the blue whales, as well as the penguins. But there are some species living in sea ice that we don't talk about very much, and they are some of the tiniest organisms that there is. And that's those little guys. These are microalgae. They are tiny plants. They are individual, they are single-celled organisms, so they're very, very small, and you can't see them to the naked eye. You have to use a microscope to be able to see them. They come in all sorts of shapes and sizes, and there are about 50,000 species that have been found so far, but we think there's probably about 200,000 different species of microalgae. Now, when they are doing pretty well and they are growing really well, they can form pretty dense communities that then change the color of the sea ice, as you can see from that picture on the left-hand side. That's us breaking through sea ice going to Antarctica, and that color that you have there is really reflective of the dense community that are growing within sea ice. So how do they do this? They live within the little pockets of brines that Ed mentioned before. So sea ice is a sort of a composite material. It's a mixture of a solid structure as well as some inclusions of little liquid, heavy saline brines within them. And within those brines, you have those algae growing in there. They're pretty impressive because the sea ice salinity can go up to about 200. The ocean is about 35. The temperature can go down to about -20, which is, sea ice freezes at -2. So they're able to live in those very extreme conditions. And then those fluctuations throughout the day, you can have differences in the salinity and temperature as the warming and melt continues within the ice, and those algae can adapt to that. So they're very, very good at adapting to those changes. What they can also do is represent an important source of food in Antarctica and in the Southern Ocean, especially in sea ice where we have those little guys called krill, which are feeding on the ice algae. And they rely on ice algae for 9 to 10 months of the year. Without the ice algae, they're not able to survive. So the whole life cycle depends on the sea ice and the algae within the ice to be able to grow. Putting aside the role of krill, sea ice can also pump, or the algae within the ice can also pump CO2, which, as you know, we've been emitting more and more CO2 in the atmosphere. And what those algae can do is, because they are plants, just like plants on land, they use the sun energy as well as the CO2 to form their bodies. And when those bodies start to die, they are exported to the seafloor. So that's what we call the biological pump of carbon. It's that mechanism of pumping CO2 from the surface of the ocean to the deep ocean. And it's quite an important process for us to understand because as we pump more CO2 in the atmosphere, those little guys are helping us to counteract those effects. What they can also do is, as they take up CO2, they emit oxygen. And about half of the oxygen you have in the atmosphere is due to microalgae. So every second breath you take is due to phytoplankton and microalgae growing in sea ice. So you can see that those algae are very small. You can't see them to the naked eye. They live for about a week, but they provide a really wide range of ecosystem services for us. Another gas that is interesting with microalgae is that they can produce what we call dimethyl sulfide. It's a gas that is produced when they are quite stressed. They use it as a cryoprotectant. And when that gas gets emitted in the atmosphere, it allows to form clouds. And those clouds then can buffer some of that heat that is coming down from the sun. That's the smell of DMS is actually what you get when you go to the sea. That smell is the DMS. Well, every time you go, oh, that smells like the sea. That's DMS produced by microalgae. So you can see how those microalgae are doing two things for us. They take up CO2, so they counteract climate change, and they also produce that DMS, which also is a climate cooling gas. So they're pretty cool, even if we don't think about them very much. So think about them when you breathe. Then within sea ice, you also have a wide range of species. We've talked about the algae. Those algae are feeding the krill that you can see on the top left corner. Krill are really interesting species because they are some of the most abundant there is. For every human being that you have about 100,000 krill. So they're huge. And they feed on ice algae for 9 months of the year. And when they feed on them, in about 10 minutes, they can eat through a patch of about 1 square foot. So they're pretty voracious, and they go through a lot of ice algae when they are growing. Then those krill, which are quite abundant and quite rich in the environment, are then preyed upon by about 200 different species of animals. And that goes from the whales that you all know, whether it's the blue whale or the humpback whales, different types of seals, as well as penguins. Fish are also billions of fish that you have in the Southern Ocean are depending on krill and feeding on krill. So you can see how the krill is really quite important in that ecosystem and that they rely on the sea ice to be able to function. So now when you think about the talk that Ed just gave before, if you're starting to remove that sea ice or changes in sea ice are happening, what happens to that whole ecosystem? What happens to the ice algae? What happens to the krill? What happens to the species that feed on the krill? It's quite tricky to know. What we know is that what we see at the moment is likely to continue. We are likely to see a reduction in the extent of sea ice, so how far north the sea ice will form. We're also likely to see a reduction in the duration, so the sea ice is likely to form later and melt earlier than it does now. And that is likely to have an effect on the environment as a whole. Those are quite tricky to get in Antarctica because sometimes we don't have a huge amount of data. We don't know much about the sea ice thickness. And that means that there are going to be some winners, there are going to be some losers, and there are a lot of unknowns for what we study. What is clear is that the loss of habitat as well as food source is going to mean that you're going to have a loss in biodiversity. So all the species that depend on sea ice to be able to function are going to disappear. You're going to then end up having a restructure of the ecosystems. If you lose some biodiversity, that's going to have that domino effect on others. We may see a disruption of the cycle of nutrients. I didn't talk much about nutrients in this talk, but nutrients are key for photosynthesis and that uptake of CO2. That would then have a flow-on effect on those climate-active gases like CO2 and DMS that I mentioned. And then that has a flow-on effect on the krill and the higher trophic levels that we all know in Antarctica. And as Ed mentioned in his talk, the loss of sea ice also influences a whole range of Southern Ocean processes like the global high-line circulation, as well as what we call the albedo effect, is when the sea ice is white and reflects the sun's heat back into space. So what can we do? What can you do? In the same line as Ed's talk, as we are struggling a bit to keep our carbon emissions down, there has been some suggestions back in the Arctic about sea ice restoration proposals, which would not restore sea ice to its natural state. And there are also some issues around the side effects from those restoration proposals. Those groups do exist. Some people are working pretty hard in trying to form or make artificial sea ice or new sea ice in the Arctic. And it's quite concerning for scientists that are trying to understand what's going on. The safest and most reliable way for us to protect Antarctica and the sea ice around it is to reduce greenhouse gas emission. So how you can get involved, I think by coming to talks like this, it's really key to engage with the community as much as possible. And as scientists, we don't do it very well. It's key to be looking at some citizen science programs. There is a great program called Adopt a Float, which is used by scientists and by students in the classroom to try to understand what's going on around the world ocean. There are some citizen science programs like Fjord Phyto, which looks at the different type of macroalgae and how they're growing in Antarctica. And we just submitted or published actually a couple of weeks ago, I think it came out, a whole special volume on Antarctica and the Southern Ocean. It's published in Frontiers for Science and Frontiers for Young Minds, sorry. And Frontiers for Young Minds is an amazing volume that is written by scientists for kids, and they're really, really useful for the wider audience. So I invite you to have a look at it, especially if you're a teacher or if you have kids, go and have a look at the Frontiers for Young Minds. They have an amazing amount of really good papers in there for everyone.
Thank you so much, Delphine. Fascinating science and really useful to have the hopeful messages around how to get involved and learn more. So our last panelist for tonight, certainly not the least, is Dr. Barb Wienecke. She's a seabird ecologist with the Australian Antarctic Division. And she's been studying penguins and other seabirds for over 30 years, participating in over 15 expeditions to Antarctica and subantarctic islands. For many years, Barb studied the foraging ecology of seabirds using satellite tracking to determine the at-sea distribution of seabirds, particularly penguins, providing important knowledge to inform the establishment of marine protected areas. So please join me in welcoming Dr. Barbara.
Thank you very much, Jess, for your very kind introduction, and thank you very much to my previous speakers for setting up the following talk so beautifully. Great to get the big picture. What we will do now is zoom in a little bit into a bit more detail. Emperor penguins have been described in all sorts of wonderful ways, and you cannot possibly argue with the fact that they are absolutely extraordinary and fascinating creatures, even though the old explorers thought they were making pretty good dinner and used them even to heat their heaters. Disgusting. Emperor penguins have been around for a very long time. Well, at least in human terms. 1 million years is pretty long. They evolved at a time when Antarctica was already well and truly frozen. And they decided, for goodness knows what reason, to set up home down there in one of the Earth's most extreme environments you can imagine. Breeding in winter. They don't just live there, they decided to breed in the winter. And in order to achieve that, they obviously had to adapt anatomically, physiologically, and behaviorally. So they really just had to, in some ways, reinvent what a penguin is. The fact that they are still around actually is indicative of their extraordinary success. They have been a really great species. Now, we don't know what happened to emperors in the long gone past, but we know that currently there are 60+ colonies all dotted around the Antarctic continent. And they vary hugely in size. Some of them just have a few hundred pairs, and others are over 20,000 breeding pairs, and most of them are sort of somewhere in between. Most of the colonies occupy the stationary land-fast sea ice, and I have to make this distinction because sea ice comprises two components. The fast ice is where the penguins set up shop, and the pack ice is where they feed. The stationary, the fast ice, as the name indicates, is quite stationary, and the pack ice just drifts around the continent. You probably all know that emperor penguin males incubate their eggs on their feet. There is no other material to build nests. That's the only chance they have. That, however, limits their mobility quite a bit. They really can only take teeny weeny tiny steps. Otherwise, they risk losing their egg. And to do this successfully, they need a relatively flat surface. But flat surfaces on land are incredibly difficult to come by. Ice-free land is incredibly difficult to come by. So the fast ice just offers a fantastic opportunity for them to set up breeding colonies. Some of those colonies are a fairly long distance away from the edge of the fast ice, so they obviously need to travel across this very lumpy and uneven landscape to reach their foraging grounds. And that requires a fair bit of energy and a lot of time. It means that some of the chicks actually have to wait about a fortnight before they get their next meal. As Ed and Delphine have pointed out, Antarctic sea ice conditions are changing rapidly. But again, the fast ice component is what particularly important to emperors. Any change in the extent or quality, and particularly the duration of fast ice, affects colonies. When all is well, we call it the happy days scenario. The fast ice is indicated by this blue bar. It starts forming, or it's pretty solid already, around about March, April. The birds come together. They have a very, very protected courtship season. Got to make sure that you do it with the right other penguin. And then between laying eggs and the chicks finally hatching, you need at least another 9 months where the fast ice has to be reliable so that the chicks can actually fledge and become independent and do their own thing. However, what we are beginning to see more and more now is indeed a shortening of the fast ice duration in certain areas. If it happens at the beginning of the season, the penguins might just delay the onset of breeding. They may even decide just to shorten this very complicated courtship period a little bit. However, when it comes to the pointy end, the chick rearing end of things become very difficult because they cannot speed up the time that it takes to incubate or rear their chicks. So when the fast ice actually gives up before the chicks are ready, there is obviously trouble at hand. And just to give you an idea what we actually see and mean when we talk about changes in fast ice, this is a beautiful satellite image of the Mawson Coast taken in September 2020, I think, December 2020, 25th of December 2020. Beautiful, and that is what the Mawson Coast used to look like. The Mawson Coast has always been known for its extensive and reliable fast ice. The area that you see there, nicely attached to the continent, was over 30,000 square kilometers. And even the thinnest part was still 50 kilometers wide. Great stuff. Was a fantastic year for the penguins. Fast forward to last year. Yes, we know it was a pretty shocking year, unfortunately also for the penguins. You can see that only a bit of fast ice is left on the western side, sort of between Cloa and Fold Island. Only about 5,500 square kilometers of ice at a time when the penguin chicks are actually just getting ready to leave. Oster, on the right side of the image, wasn't devastated, but the chick losses there would have been higher than when the ice had still been there. So what you see there is just incredibly broken up and smashed ice. No colony can possibly exist on something like that. Another example is the Ninnisbank colony, which is located on an extraordinary piece of fast ice that has a very small attachment to the coast, but it extends about 170 kilometers north, like a finger sticking out of the continent. 175 kilometers is all the way from here to Lorne. So it really is a long way. And you can already see in the lower part of the image, there are some rather substantial cracks. Now we are just talking September. This is still in the middle of the chick rearing season. The little chicks are only just become visible and start crashing. And so one started to get a tad nervous about this. And unfortunately, it didn't even take another month and the entire area was gone. By the 23rd of October, there literally was no fast ice left. This picture was taken on the 8th of November. That was the first high-resolution satellite image that we got access to. And it gives you an idea of how mobile probably the pack ice actually is. The colony area had been completely ice-free in October, and you can see that the pack ice has already moved in. So not good. What is particularly disconcerting is that Oster and the Ninnisbank colonies are not the exception. We know that in the past 8 years, at least 30% of all known emperor penguin colonies have suffered this experience, and some of them as much as 3 times. So that can't be good news. The increased frequency of such events is what is particularly disconcerting. What does that mean for the colonies? Let's go back to our happy day scenario. Even in the happy day scenario, every now and then there would have been a year where things just went horribly pear-shaped. However, there are long-lived seabirds and they can actually recover from something like that, provided it doesn't happen too frequently. However, as greenhouse gases continue to increase, our temperature continues to increase, and that means that there is a fairly good chance that the hot Earth scenario is becoming not only more likely, but possibly even the norm. And if you cannot rear your chicks to fledging, you cannot produce recruits that are going to sustain the colonies. So that is unfortunately pretty bad news. Now, emperor penguins are trying their utmost to adapt to the changing colonies, to the changing conditions. Some colonies had repeated breeding failures. They collectively, and don't ask me how they did it, packed up their bags and moved elsewhere. But you have to find alternative colony areas. That is also not that easy. Another interesting approach is that some of these colonies have actually decided to move on top of an iceberg. Really? You know, I mean, as in, wow. It might sound great to live on top of an iceberg, but of course it comes with its own challenges. One of them is you have to have access. And where there is a snow bridge or maybe some ablated ice that gives you access, who knows how long this is going to last. When the access route disappears, you are either stuck on top of it or you can't get back up. Really bad news. You may also just be able to make out some crevasses. Crevasses are just dangerous. The little ones are worse so than the big ones. The big ones tend to fill up with snow, but the little ones often have only relatively thin snow bridges. And when you happen to step on them, you might just find yourself in the abyss before you know it. The other thing is, that, as you can see in this image just beautifully, the winds are ferocious. They are just relentless. I know about it because I got blown off my feet more than once. So such intense wind exposure means that they actually have to work much harder to maintain their body temperature. That requires a lot of energy. Climate change, without doubt, is the most serious threat to emperor penguins. And the speed at which things are changing for them may indeed be faster than these birds can adapt to. I mean, think about it. In the last million years, they must have gone through at least 8 cycles of warming and cooling. The temperatures at some point were probably 7 or 8 degrees above what we experience now. But what is so important is the rate of change. It took 5,000 years before these temperatures were reached. Now we have managed to increase the global temperature by a degree in a century. You do the maths, it's not looking good. So the only thing that really is going to help emperors is if we somehow try to find a way to reverse it. So their future is very much in our hands. Thank you.
Thank you, Barb. Very sobering. That's the end of the talks, and now we will move on to questions. So I'm going to invite our 3 speakers to join me on these very high stools. And so in the room, if you know who you would like to answer your question, please feel free to address it directly to them, or I can help facilitate that. So yes, let's go ahead.
The difference between climate change and climate warming and the relationship between the two. Could you expand on that?
You're looking at me, so I assume. I guess in the current scenario of anthropogenic climate change, it is a climate warming. As Barb alluded to, there have been cycles of climate change in the past, glacial and interglacial, where we warm and then we cool. In the current context of human-induced climate change, it is a global warming. Now, the climate system is pretty complicated and it wobbles around in all sorts of mysterious ways. So even within a warming world, there are places that will get colder for a little while. But in general, the average trend is a warming trend at the moment.
And does that affect the storms? And...
The short answer is yes. The longer answer is probably another series of talks about how climate change impacts fire weather and storms and things like this. The short answer is that as the world warms, we expect dry places to get drier, which contributes to more intense fires, wet places to get wetter, contributing to more intense rainstorms and rain events. So yes, in general, we expect these things to get stronger and to get worse under a climate change scenario.
Thanks, Ed. So we'll go to an online question next, and maybe this is one to pass to you first, Barb. And the question is, what impact will the current harvesting of krill have on the food chain? Well, I think the question is, what's the implications for the ecosystem of taking krill out from the food chain?
So krill is an interesting one. So the krill is really relying on the sea ice, and we know that things are changing already. So we've observed, especially in the West Antarctic Peninsula, a contraction of krill towards the south because the waters further north are warming. And so what can happen then is other species like salps can take over. And salps are a lot less nutritious. They're gelatinous. They're a bit like not seaweed. What do you call them? Pure. Jellyfish, thank you. My French is struggling. And so you can see a change in the type of food that is becoming available. So some species don't care what they eat as long as there's food, but in general, salps are a lot less nutritious than krill is. So that can have a flow-on effect on the health of the whole ecosystem.
Thank you. But did you want to add anything for the emperor penguins, Bob?
Well, I can just add that is possibly one thing where emperors have a little bit of an advantage. Their cousins, the king penguins, are highly specialized feeders. Most of their diet comprises of lanternfish, but emperor penguins seem to eat just about anything that dares to swim past them, So they do consume krill, but they really have a greatly diverse diet, which might well help them to cope with any sort of fishery impact.
Thank you. We had one here, I think.
That fairly distinct drop in sea ice in 2015, 2016, and then again last year. Is that any particular identifiable cause? It seems like it wasn't a gradual thing, just all at once. Do we know what was that?
That is a great question. We have a few ideas. We know that there was warming beneath the surface of the ocean, sort of a couple of 100 meters down. That area has been warming, and the places that warmed more strongly had that strong sea ice reduction. Understanding exactly why it was that in 2015 and 2016 we had this massive crash and why in 2023 we had another is an open research question. The sort of glib answer is climate change, the world is getting warmer, sea ice is going to reduce. But why it happened so rapidly in those punctuated events is one of the open research questions at the moment.
Back to online, we have one about Galapagos penguins. And the difference between the penguins in the Galapagos Islands and emperor penguins.
Well, that is a very nice question. You know, I like Galapagos penguins. The interesting thing is that one could say that a penguin is a penguin. They have a lot of adaptations that are present right throughout the entire family of penguins. For example, their bullet-shaped body shape. You know, you cannot improve on the design of a penguin shape. They are so incredibly hydrodynamic. Now, the work has actually been done. It's remarkable. When you think that an Adelie penguin has probably the same resistance in water as a 10-cent piece. They are remarkable. So they don't have sweat glands. That is the problem with Galapagos. Actually, no penguin has sweat glands. They obviously live in a very, very hot climate, which is why they have adjusted their behaviors more than their anatomy or physiology. They need to have a certain anatomy and physiology to live in the ocean. But they tend to burrow, and burrows seem to have much more of an even climate. You know, we should all be living in burrows as far as I'm concerned. The climate is or the temperatures are much more even. And they also tend to spend the hottest time of the day in the water. Makes a great deal of sense.
In the middle here, we had a hand.
My understanding is that we're on a trajectory of an RCP 8.5, if I'm not mistaken. And what sort of hope is that, you know, given our current emissions, and as you mentioned, you know, the only way sort of, you know, if we all do something about it, or is it now just all about adaptation? And as humans, you know, we can put air cons on, but I don't know about the other species, especially down in Antarctica.
So the good news there is that RCP 8.5, the representative concentration pathway 8.5 from the previous round of CMIP models, looks to be a little bit high. We seem to be coming in underneath that pathway. So it is not as bad as that. Obviously, that's only limited good news, saying that it's not as bad as this pretty catastrophic scenario. But it's not as bad as that. Why should we hope? Well, I choose to hope. There's this idea of radical hope that even in the face of whatever is unfolding, we can act to make the future less bad, that through our actions, we can improve that future. If you don't have any hope for the future, you're not going to do that. So there's a lot of talk in the media about tipping points in climate change, that you reach these points where something irreversible happens. Yes, that's scary. That's terrifying. We're not sure that we've hit any of those yet. We should use that as motivation to try and avoid it, to keep our warming as low as we can. But also, even without that tipping point idea, we still know what has to happen. And every molecule of carbon dioxide we put into the atmosphere warms the Earth. Every molecule we don't emit is a better future that we're working towards. That's how I see it.
Actually, that's a good segue, I think, Ed, too. I was going to combine a couple of the questions online. One which is about, this comes up a lot, I think, in our climate conversations. What are some of the practical things we can do on a day-to-day basis? And the other one is about keeping positive, which you've started to answer, Ed. So maybe we could, everyone on the panel could have a crack at those two things. What's something to do in day-to-day life to address the climate crisis in some way, and how do you keep positive about it?
Yeah, it's a tricky one. I think as a scientist, sometimes we struggle to stay positive because when we look at the data, it's a bit difficult to stay upbeat, but we kind of have to keep going. That's our jobs. And if we can then relay to the audience like we're doing today, it's helpful. I think a key thing for us scientists is to talk to governments. Often politicians see the next election campaign and they don't really look in the future on the long term. So I think as a community, if we can make pressure on politicians, then things will get probably a bit better for us, because a lot of the problems that we have, we can solve things at individual, but it needs to have a collective approach to it. It needs to be enforced. It needs to be pushed. And that's happened with the CFC, for example, for those who are from the 80s generation, like myself. Back in the 80s, we had a big problem with the ozone hole, and that was all over the news. And we banned CFCs. Like, that happened. We did ban them, and we've seen a resolution in the ozone hole. So CO2 is a much bigger problem than CFCs, but it can be done. And I think that's how we try to stay optimistic, I think, as scientists. It can be done. It takes a lot of people to be able to do it.
So I agree with everything that Delphine and Barb have said here. I think the most important thing that we can do is vote for people who take it seriously. That, more than anything else, is going to help set up systems in which your individual choices are easier, where you live in a world where it is possible to make choices that don't produce more greenhouse gas emissions. Having said that you should vote for people who take it seriously, there are things you can do in your personal life, as Barb and Delphine were alluding to. We know what a lot of those are. If you own a house and you can afford to put solar panels on it, that's great. If you can buy an electric car, that's great. If you can walk or ride the bus or ride a bike, these are all good choices. They're less important than setting up a system which brings everyone along for success, but they help and they're worth doing.
Just one more thought. I hear far too often of people who despair. I can understand that. And they say, oh, well, there's nothing I can do. But we should never, ever underestimate the collective power we all have. If everybody does their bit, it is remarkable what can be achieved, which is precisely what Delphine said. The CFCs, thank you. We can live quite happily without them. There have been alternatives, but I think we also have to be a little bit cautious to put all our hope into the technology basket. I really think that it requires a change in attitude of what we actually consider important in our lives.
I'm loving this applause. It's very heartening. And apologies online. I think when the mic was off, online might have missed a little bit of your first response, Barb. There was a fantastic analogy to blowing out a candle in a burning house, and where are we doing that versus actually putting the fire out, which I think is really powerful. Lots of questions here. I'll go at the back there. Yes, you. Yes.
Just wondering why war, the increase in the incidences of war and the greenhouse gases they produce, like Ukraine and Israel and things like that, that could have exacerbated the rise in CO2 levels. Plus, Tasmania burns the forests. So, there's a whole heap of stuff that adds to it that's, if you changed it, it would make a massive difference.
Does anyone want to respond? I think that is probably more of an observation, I think, than possibly outside the specific expertise of the panel. But yes, thank you for that. We might go to a question in the room. Is there one over? I've been over this side a lot and I'm conscious I'm not. Yes.
I have a question for Professor Delphine. Have you been able to grow that microalgae in the lab? And if yes, it's very hard. Or...
The phytoplankton, so the microalgae from seawater, we are able to grow them in the lab and keep them happy. The sea ice algae are a lot harder because you kind of have to keep them within sea ice and grow them within sea ice. We managed to grow some sea ice artificially in the lab. It's not great because you can't reproduce the environmental conditions that well. So you end up forming sea ice that has very different texture. You don't have the same light level. You don't have the same nutrients. So it's quite hard to reproduce, which means that we have to go in the field to be able to study them. So we do tend, when we go in the field, to collect some ice algae and do some experiments on them in the field. But that's why it's quite hard to study, because we don't have a huge amount of data.
We have a question online about relationship between sea ice and katabatic winds. So the question is, how much does the change in sea ice affect the katabatic winds? But maybe a more general question about whether there's a relationship there, if anyone would like to talk to that. And actually, if another question, if it's relevant to address at the same time, about implications for changes in global ocean circulation. So I don't know if you can wrap them together cleverly, Ed. No pressure.
I can't promise to wrap them together cleverly. But The katabatic winds are this incredibly persistent feature where we have winds flowing off the Antarctic continent, so sort of northwards in general, from the land out towards the ocean. I wouldn't really think of the sea ice affecting the katabatic winds. It sort of works the other way. The winds push the ice away from the land, and that leads to a region of open water in this incredibly cold, frigid, dark environment. And so these are sea ice factories. These are places where we grow lots and lots of sea ice, and it pushes away north because of the wind. So these are areas called polynyas, and they're incredibly productive. They have lots and lots of the little algae that grows there, little fish, all sorts of things in the food web. So the katabatic winds help us produce lots of sea ice and move that sea ice northwards away from the continent. As I talked about, when sea ice forms, it produces that cold, salty brine. So these places are also places where we're forming the really dense, cold, salty water that sinks down into the ocean abyss away from Antarctica. So the katabatic winds, by influencing sea ice formation, help influence these global circulations in the ocean, these global ocean currents. I think that's the best I can do to wrap them together.
Great, thank you.
Yes, I'm sorry. I had a suggestion for Professor. We spoke tonight about the reflective capacity of the ice, and any physicist will tell you that a white or a silver roof will reflect the sunlight back to the sun. If you have a black tile roof, it absorbs the sunlight during the day and gets extremely hot. And in my generation, we built terracotta tiles in the sunroom to warm up during the winter day, and that at night radiated heat to warm the sun at the house. Your black tiled roofs, your black tiled roads, your black tiled asphalt airports all absorb heat during the day, and at night they radiate that heat back into the atmosphere, not through the atmosphere as the sunlight coming off your moving ice fields. Now, there was a report about 6 or 8 months ago on that exact point that the scientists, maybe yourself, was lamenting the loss of a ice field multiple size of Tasmania, as we've seen on your schematics tonight. And in America yesterday, they've got a heat wave. What are they doing? They're painting the roads white. What did they do at the Australian Open this year when it was 39 degrees in Melbourne? They painted the footpaths white. Now, I've got a challenge to you. That if you could reflect the sunlight back from a silver roof or a white roof or a white road, and we've got one going up southern out that goes along the turn up to the Vincent Saddle, that's a white asphalt road, and that will not be as hot as that black form would be here as this white form is. Now that is a whole new challenge. It is a global warming aspect. It's nothing to do with CO2. It is a fact that every black road, every black roof absorbs heat during the day and puts it out into the atmosphere at night when we should be cooling down. I give you that challenge.
See what I can do. Yeah, as far as the sea ice goes, it's really a key thing, because if we lose sea ice, then that that's what we call albedo. So it's that reflection from the white back out into the atmosphere. If we remove the sea ice, then you end up with a dark ocean that will absorb more heat, and then it will form less sea ice. So that's the problem we're having now, is that we're trying to break that loop cycle where you're losing sea ice, you absorb more heat, then you're forming less sea ice, and then you end up rolling, you're in big trouble. And that's what some of those researchers have been trying to, or not researchers, but groups of geoengineering want to do is work on that reflectiveness of the sea ice. So they want to make it as white as possible, which we probably will have a problem in the future, is that we might see more rain rather than snow in Antarctica. And if you start having rain on top of sea ice, that will change that reflectivity of the sea ice. So it will make it absorb even more heat, pretty much. And then you will start melting it even more. So it's not only just the way that the extent of sea ice is changing, in our case, or the duration that sea ice is there, it's also the type of sea ice that we're going to have is another problem that we're having. Yeah, but definitely white is the way to go.
Online, Barb, we have another penguin question. And this question is asking, with the melting of sea ice, how will this affect emperor penguins during molt?
That is a very good question. I was thinking about including this in the talk, but I'll be probably still talking if I had done that. The molt is a very, very important time of year. It happens in adults usually after the breeding season. These birds have been wearing the same feather coat for nearly 12 months. And believe me, when you're exposed to storm after storm and you're swimming in salt water all the time, those beautiful feathers get pretty worn and they need to be exchanged. And emperor penguins, like all penguins, undergo what is called a catastrophic molt. They will change every single feather on their body, and there are thousands of them, within about 3 to 4 weeks. During this period, they are no longer waterproof. If they were to go into the ocean, they would probably become waterlogged or hypothermic. In any case, they would probably not survive. So during the molt, they have to stay out of the water, which means if you're fasting for a month, you have to make sure that you've got the body reserves to cope with that. The trouble at the moment is that they are molting around about February, which is generally the time when the sea ice, or the fast ice in particular, is at its minimum. So they're already looking pretty desperately for spaces where they can haul out, because if they can't go into the water, they have to sit either on islands. Most of them are pretty steep and quite difficult to get onto, or they have to find themselves teeny weeny tiny areas where fast ice still exists. Sometimes they do indeed, again, climb onto sea ice, or onto icebergs where it is possible. We had a horrible situation in the Bellingshausen Sea in 21 and 22, where 5 colonies lost their fast ice home altogether. It was a complete wipeout season for 5 colonies in the same area. Absolutely dreadful. Tens of thousands of chicks probably died. When I looked at the satellite imagery, I kept thinking, where on earth are these adults going to molt? Because that is an area where these very steep ice cliffs are just abundant, and there are absolutely no islands. So the trouble is, I only talked about the potential of losing chicks, which means that, the adult population is going to continue for a while yet. They are relatively long-lived. But when we actually have a situation where the adults can't find safe molting places anymore, and we're losing our established breeders, then that is going to be an entirely different ballgame that we're playing. And that is a serious issue. Thank you very much for that question.
With the bright T-shirt kind of middle right.
So I'm just thinking that, so I've seen that somewhere in Australia, they're doing like little ponds or like pontons, floating places for the seabirds or just birds here. Would we be able to make something like that for the penguins that are flat that we can put out, or would it just like, glaze over when the ice comes in?
Are you a geoengineer?
Unfortunately not.
Look, of course, I mean, what are we going to do? The trouble with platforms is that they would have to be put into 200-300 meters of water. They have to be home to up to over 22,000 birds, so it is something that I've often been wondering about, can't we just put platforms out there? But the expense would be horrendous. And keep in mind that when you have a coast that is pretty much ice-free, the storms are just vicious. And how on earth would you secure anything against those mega storms? But keep thinking, you might come up with a great idea.
I'm a biologist, unfortunately. So,
Thank you. Back online, I'm going to have another go at seeing whether we can, this is for you again, sorry, Ed. But it does lead on from what you were talking about before. So people are specifically asking about longer term implications for global overturning circulation. And there is another question about whether there's a connection to what's happening in the Arctic, but I suspect that might be a bit too much of a push, but feel free to,
All right, we'll see how we go. So I mentioned that this global overturning circulation, our best estimate is that it has slowed down by about a third since the 1970s. It's quite hard to model this really accurately in our computer simulations because it relies on quite small scale features. Those polynyas that I mentioned before happen on just a few kilometers, maybe tens of kilometers. And when we run the climate models for these climate projections, they're grid cells, they're little blocks in which we solve the equations, are somewhere between 50 and 100 kilometers square. So representing those processes that happen at small scales is quite tough. Having said that, we can use these models as our best tool. They are the best tools that we have available, so we should look at them and we should try and understand what's going on. We can also run higher resolution simulations. They're just much more expensive. There was some work in Australia in the last couple of years where people did run a much higher resolution ocean model for about 50 years into the future. And they included projected melt of the Antarctic ice sheet, projected changes in the atmosphere and the winds, and they tried to understand what that ocean circulation was going to do. And what it did was it just decreased in strength pretty consistently and constantly throughout that whole 50 years of simulation. So it's already slowed down by about a third, we think. They showed another 50% reduction in the next 30 to 40 years. I don't think you can add those two numbers together and say, well, that's it, it's up to an 80% slowdown. The system's a bit more complicated than that. But all of our evidence suggests that this global overturning circulation, the deep part of that circulation from Antarctica, is weakening and is slowing down. A very similar thing happens in the North Atlantic. You form this cold, salty water through sea ice growth, and ice sheet melt off Greenland contributes lots of fresh water to the surface of the ocean, and that reduces the saltiness of this water that forms. And so it slows down that North Atlantic component of the overturning circulation. If you've ever seen the movie The Day After Tomorrow, you don't know what happens when the overturning circulation changes. But it is a great representation of the global scale of these changes. The rate, the pace at which that change happens is not real. That's very much a Hollywood blockbuster. But it does convey the sorts of extreme changes that we expect to happen on the global climate. There will be big ramifications from changing this overturning circulation because it moves heat around the world. And heat is what keeps us warm. So changes to the sea ice in the Arctic and the Antarctic will contribute to a slowdown of these overturning circulations. Exactly how quickly that slowdown happens is somewhat uncertain, but it's the destination that we're heading towards.
Do you want to add anything to that from the nutrient transport perspective, Delphine?
Yeah, that's a tricky one with the nutrients. So as Ed mentioned, the global circulation does redistribute nutrients all around the world, and that can affect the productivity in the water. So those microalgae growing and taking up CO2. And as the waters are more productive, then you end up having more fisheries industry. So that kind of have a flow-on effect on the food that we can get from the oceans as well. So everything is interconnected, I think. And in the Arctic, the interesting thing is that there's a lot more data in the Arctic than we do in Antarctica, to be honest, at least with the sea ice aspect. The two are very different. So the Arctic is a sea surrounded by continent, and the Antarctic is a continent surrounded by oceans. But the Arctic has seen some pretty extreme changes in the last 50 years. They've seen a lot of loss of that multi-year ice. So the sea ice over there is not forming and melting every year like in Antarctica. It's meant to be multi-year, where you have 1 year just adds on another. So you end up with 10, 20 years of sea ice. And over there, the loss of that multi-year ice is really concerning. We're getting more into a state where it looks more like Antarctica than it does what is meant to be in the Arctic. So there's a lot of work in that space.
Yes, that was.
Ed, a sort of carry on from what you were speaking about before in terms of the ocean circulation. I wonder if you could speak about the relationship between sea ice and ice sheets and sea level rise.
That's a wonderful question. So I didn't get into the relationship between sea ice and ice shelves and sea level rise because when you give a short talk, obviously things have to get cut. So Barb has mentioned that the Southern Ocean around Antarctica is this incredibly stormy place. We have strong winds that blow over vast stretches of ocean, and they produce really enormous waves. When those waves hit the sea ice, they lose their energy. It damps them down. And so rather than waves crashing against the ice cliffs of the ice shelves or the coastline, they lose all their energy in the sea ice. But if you take that protective belt of sea ice away, then you get lots of storm damage on the ice shelves. There have been regional case studies that have shown ice shelf collapse following a loss of sea ice in that area. Now, taking away an ice shelf doesn't directly impact sea level rise because that ice was already floating. It's the big floating extension of the ice sheet that sits on Antarctica. But if you take it away, it no longer buttresses, it no longer supports that ice sheet and keeps it on the land. So the ice that is up on the land flows more rapidly into the ocean, and that accelerates sea level rise. So there are a couple of steps in that chain to get from losing sea ice to accelerating sea level rise, but we're pretty confident about that mechanism.
If that's okay, another question to that. What's the latest modelling telling us about where that's taking us?
Where's the latest modelling on sea level rise? That's going up. That's the broad answer. I'm going to get into a couple of details. So there are a few things that contribute to sea level rise. One is that the ocean expands when it warms, and we've been warming it pretty rapidly for a while now. As that ocean warms, the water expands, and that causes the sea level to rise. When you melt the big chunks of ice sitting on Greenland and Antarctica, that ice flows into the ocean and causes sea level to rise. So these factors all contribute. What we haven't seen so far is a lot of melt from what we call East Antarctica. That's the giant chunk of ice sitting on the eastern half of Antarctica. That's really good news because that area contains enough ice to raise global sea level by about 55 meters. Yeah, 55. West Antarctica, where we have seen ice loss and accelerating ice loss, only holds about 5 meters of sea level rise. So that's comparatively good news. But in that area, we are seeing warmer ocean waters coming up underneath those ice shelves and melting them from below. We're seeing these rapid reductions in the sea ice protective belt around the edge. So we expect in the future that the waves will damage those ice shelves, icebergs will carve off more rapidly, and will melt it from below more rapidly. Both processes contribute to an increase in the rate of sea level rise.
Sobering again. Back online, we have a couple of questions now about so kind of interacting effects of non-climate stresses, particularly tourism. So maybe for you, Barb, to start with, what kind of implications for Antarctic wildlife might there be in relation to disease risk or pollution of tourism in Antarctica?
Well, I think the trouble is, wherever we as humans go, we have an impact, whether we want to or not. How heavy the impact is entirely up to us. And Arctic tourism is still very much a growing industry. It took a bit of a dive during COVID, as you can imagine, but it is up and flourishing again. A lot of the operators are very conscious of their responsibility, which is great in terms of the bird flu, which a lot of people are deeply, deeply worried about. Because if that hits, good grief, again, that is a completely different level of playing field that we're talking about. But they're very good in implementing biosecurity measures. Everybody who goes off board has to wash their boots very thoroughly. Any tripods or anything that touches the ground has to be cleaned. So the tourism operators, at least in that regard, are doing very, very well. It is a bit of a worry that the numbers are still increasing because the other factor is, of course, disturbance. Everybody wants to go and see the penguins. Some people even want to sit in colonies, which is a really bad idea. So I don't think we can stop it. I'm not even sure that we should stop it because sometimes people need to see what they try to protect. But on the other side, if everybody were to go down there, wow, the impact would be horrendous. So it's, as with everything in life, quite a balancing approach that we have to take. But again, a lot of the tourist operators are very, very cautious in what they do. And, people like myself are forever grateful for that.
I'm really sorry, we're out of time for questions. Thank you for all the wonderful questions and the excellent responses and a really compelling combination of the stark facts, but also options for hope. So thank you. I would like now to invite Khalid Tozer and Kathy Allen to provide a vote of thanks on behalf of the Australian Meteorological and Oceanographic Society.
Thank you. Thanks, Jess. We just really wanted to thank our wonderful speakers and MC tonight. It's really interesting presentations and a discussion after. So thank you. We've just got a little little token to show our appreciation. Well, that's happening. Just a quick note about the Australian Meteorological and Oceanographic Society, also called AMOS. It's a lot easier to say. So we put on this, sort of helped organise this event along with the University of Tasmania. So AMOS represents the atmospheric and oceanographic sciences in Australia and acts as a credible, independent voice for the profession. Membership of the society includes scientists employed across the climate sciences, but also extends to teachers, students, retired scientists, and the general community with an interest in meteorology and oceanography. Oceanography. I'll move on, you know what I mean, the oceans. AMOS's vision is to advance the scientific understanding of the atmosphere, oceans and climate system and their socioeconomic and ecological impacts, and promote applications of this understanding for the benefit of all Australians. The Society provides support for meteorology and oceanography through publications, meetings, grants, prizes and public events, just like this one. So if that sounds interesting to you and you'd like to join AMOS or chat a bit more about it, you're please welcome to come and see Kathy or myself tonight. But also, yeah, feel free to go and have a look at the website, the AMOS website at amos.org.au.
Thank you so much again. That time just flew by with very many excellent questions and fantastic responses. We're pretty much at the end of our evening. Certainly we've, heard some alarming science around the currently, the critical changes that are currently happening in Antarctica and the Southern Ocean. And, the pressing need for the world-class science really that happens here in Hobart to understand and provide options to respond to those changes. I'd also invite you to consider that Antarctic ice environments aren't just a critical barometer for our global climate health, but their fate is intimately tied to the future of, our climate system and life on Earth, including our own. We have a collective responsibility to protect our planet's vulnerable ecosystems, and we have the power to make choices about the impacts of our actions on the world. The University of Tasmania's Islands of Idea program brings you this conversation in the hope that our community of knowledge lovers will share this conversation, because if many of us make small changes, then the impact is great. But if many of us actively seek better solutions to the climate crisis, then the impact will be significant. And so it's on that note that I remind you that this evening's talk will be available soon as a video and a podcast you can share with all of your friends. Please head to the Island of Ideas webpage for details. And while you're there, if you would like to, you can register for the next free event on Australia and the Antarctic Treaty, very relevant to some of the themes that emerged tonight. This will be the 2024 Philip Law Lecture delivered by Emeritus Professor Marcus Howard at the Australian Antarctic Festival and brought to you in partnership with Antarctic Tasmania. So you can catch Marcus's talk online or join us in person at the Stanley Burbury Theatre on the 22nd of August. So now please join me one more time in thanking our fabulous speakers, Ed, Delphine, Barb. Thank you from me to all the behind-scenes organisation that you don't see but makes these things run so smoothly. And thank you for taking part in this special event. On behalf of the University of Tasmania, have a happy and safe evening and good night.